Hi guys, Mark from Dynex Hobby again. Today I'm going to demonstrate how to perform a two-plane balance with our impulse balancing system and a new cradle that we've designed. This cradle is actually manufactured from 6061 aluminium. It's a very solid cradle. It works very well for this kind of application. So we'll go through that today. So just to give you an overview of the setup, we have a rotor, a two-plane rotor, which is essentially like a dumbbell arrangement, and we have a motor drive mechanism to spin the rotor. We've got the Impulse 2, of course, and a standard Windows laptop. This laptop is running on Windows 10, but earlier versions of Windows is still supported, but generally Windows 10 works very well with this kind of setup. Okay guys, this is our new balancing mount. This is actually in development at the moment at Dynex Hobby. It's a very solid mount, as I mentioned previously, made out of 6061 aluminium. It's very solid. It's a kind of mount that you want to use when you're balancing something at a higher precision. So I'll just move around so you can see what it looks like. So you can see that our accelerometers are mounted on each plane. So that's looking at plane 1 there. I'm going to rotate around and you'll see the accelerometer for plane 2 mounted as well on the back. Now, one thing to note is that when you're mounting accelerometers, the tails of the accelerometers should point in the same direction. That's very important because that actually determines the orientation of the final balance solution. So on the dumbbell rotor, you can see there's actually a belt mounted in the center. That belt is connected to a drive motor down below, and that drive motor is powered by a brushless speed controller and a battery. You'll notice that on the rotor itself, I've got a series of markings. I've got a few different markings here. I've got one at the top, one there, a white one just there, and also another black marker on the shaft. I use that to determine, which one will give me a good signal for the infrared sensor, or in this case, the laser module. That is actually our reference for the balance, so that when you perform the balance, the reference mark identifies, where the correction weight should go relative to the shaft. Now, installing the impulse is fairly straightforward with this setup. I've actually got this end closer to me is plane 1 and the one aft is plane 2. Just simplicity. You can arrange it any way you like, but I find it easier if the one closer to me is plane 1. So the accelerometer on plane 1 is connected to the Excel number 1 port, shown there, and the black wire actually faces the label. On plane 2, that accelerometer is mounted to Excel number 2, and again the black wire is facing up towards the label, and the laser module is connected to the infrared sensor port. Next to the ports, you'll have a select switch, and we use that to select between planes 1 and 2 during the balance. So I'll just pan over. The Impulse 2 is connected to a standard Windows laptop, and it's just any free USB port that you have available. So now I'm going to go ahead and start the Dynex Hobby software. So click on the icon on my desktop, click on the warning. So the software has a new format with our new logo. The latest version that we have as the time of recording this video is version 6.7. So the software is broken up into 3 parts. We have the single plane, 2-plane and tools. In this tutorial today, I'm actually going to demonstrate the live 2-plane balance. So I'm going to go ahead and click on that. Okay. And so this window will appear, and I'll just minimize the main window at the back. So you'll see that with the live 2-plane balance, you have two sets of clocks on the left-hand side, and these, I guess, clock faces represent the plane 1 and plane 2 of the rotor. Now, plane 1 is actually looking from the forward end of the rotor, so looking from that direction. Plane 2 is looking from the rear end. Okay, so I typically get questions as to orientation, so just recall that face is looking that way in the software, and that face is plane 2 in the software. So now we can actually go and select our device. So we'll go to Devices, select the microphone USB audio system, which is the Impulse 2, go OK, and click Start. Now, the very first thing to do is, when you activate an Impulse, is to let all the sensors rest and then click 0. And so what that does is it removes all the noise in the system and sets the readings to 0. So then we'll migrate over to the setup. Now, for this particular test today, we're going to have to identify the geometry of the rotor in order to perform the balance. Now, why is that so important? Well, the geometry actually helps identify, the balance limits, I suppose, for the system. Alrighty. So in the software, it actually asks you to measure the distance between the two mounting bearings and then the distance between the two planes. So with a rule, we can measure the distance between the bearings, between there, and then also the distance between the balance planes. So it'll be there and there. And we enter that into the software to identify the size of the rotor. So I'm just going to move this over and just walk through the entry for this form. So the rotor in today's test is going to be spinning around 4,200 RPM. The mass of the rotor itself is about 300 grams, and a balance grade I'm going to use is about 2.5. Which is about right for this kind of setup. Now, as mentioned previously, the bearing distances, I measured them and they were 60 millimeters apart, and the distance between plane 1 and plane 2 was 80 millimeters, so I'll put that in. Now, the plane 1 mass radius is the distance from the center axis of the shaft to where you're going to be placing the trial weight. So in this case, it's going to be 28 millimeters from the center of the shaft to where I'm going to be placing the mass for plane 1. And it happens to be the same for plane 2, and that's because the rotor in this case is symmetrical. So in terms of the spin direction, I get a lot of questions about this. The spin direction is relative to the actual laser module. So the laser module is facing essentially plane 1 at the moment. So if I was to spin the rotor now, so the rotor is spinning in a counterclockwise direction relative to the laser module. So that will be anti-clockwise in the software. So you'll see other windows pop up. The signal tab is associated with the actual raw vibration signal. We've got frequency as well for recording the frequencies coming from the main vibration signal. We have another tab called cross correlation. That's more for it's a new method that we've introduced to identify the phase measurements in a noisy environment. But in this case today, we're going to be focusing on the traditional method, which is a trigger method. We've got a series of gauges as well, and the advanced tab. Now for this kind of balance, we can leave the vibration factors as a default, as they are. And that should be good enough for what we want to do. Now, In terms of the corrective action, I'm going to add weight today rather than remove weight. It's a lot easier to add weight using Blu Tack or plasticine and see how the balance performs. Now the speed sensor I'm using is the infrared sensor, or the laser module in this case, which is the same thing. And the phase method, as mentioned previously, is just a trigger. And that works well for this kind of setup. So I'll go back to the live window, and you'll see in the live window you've got the live vibration vector, and that's just essentially the magnitude of the vibration and also the phase of the vibration relative to the reference marker on the shaft. Alrighty, so the very first thing to do in the balance is to calibrate the system. Now what the calibration does is it actually builds a mathematical model of your balance setup. So it includes the things like the position of the sensors, the weight of the rotor, the type of balance mount you have, all that kind of stuff gets taken into account. So the calibration really is training the Impulse software or the Platinum software to identify what an imbalance looks like in the system. Alrighty, so to carry out the calibration procedure, what I'm going to do is click on the calibrate button in the software and just cancel that. Alright, so you're going to see a series of tabs. There's an intro tab which describes the process, and then you have tabs step 1, 2, 3, and then our final calibration factors. So in step 1, it actually asks you to measure the vibration of the system with no weights attached. So what we're going to do is we're going to spin the rotor at our balancing speed. So I'm going to activate that. Make sure the impulse is selected to plane 1. So the system's now ramping up. It takes time for it to get to speed because it's a heavy rotor. So we let it ramp up, and then once the dials start to settle down, we'll take our reading for plane 1. So just waiting for that to settle. Alright, so I'm going to click on that reading for plane 1, and I'm going to switch the impulse to plane 2. And when you switch to plane 2, you notice that the phase angle starts to shift. And that's because the imbalance on plane 2 is different to plane 1. So it's what you would expect. So when that settles, I will click on plane 2, and then I can slow the rotor down. I'm going to switch back to plane 1. Right, so then I'll move to step 2. Step 2 says to apply a trial weight to the system. And the trial weight is used to teach the impulse system on how to recognize, a mass on the rotor. So what I have is a Joule scale. It's quite a sensitive scale. Its accuracy is 0.001. So I'm going to get a small piece of Blu Tack. So that's what I use for a lot of my trial weight, Blu Tack. That's available in Australia. It's a very tacky sort of plasticine. So I'm going to turn the jeweler's balance on, and I'm going to take a piece of Blu Tack and I'm going to place it on the scale. So this measures around about 0.1. I might add a bit more. Okay, 0.17 grams. So what I'm going to do is I'm going to enter that into the software. 0.17 grams. Okay, I'm going to take that off, move that across there. Now I'm going to mount that piece of blue tack onto plane 1. So I'm going to rotate the rotor around until I see the markers, and I'm going to mount the trial weight on plane 1. Right, now that trial weight is in line with the reference markers. In other words, it's actually at the 0 degree angle location. So it goes 0 degrees, 90, 180, 270, and then back to 0. Right, so now what I'm going to do is run the system at the test RPM. Make sure that my impulse is set to plane 1. Now I'm going to wait for the rotor to settle down. It is a heavy rotor and it takes some time for it to reach its speed. So it's slowly ramping up. Now you can see that the vibration vector is very stable in that location. When it stabilizes, you know that your readings are about right and it's time to take that recording. So I'm going to click on record plane 1. I'm going to switch the impulse now to plane 2. And going to wait for the readings to settle down. Now in the software, as it's taking the measurement, it's doing or performing an average calculation. That average calculation really is to eliminate a lot of variability in the measurements. So you can see that my RPM is getting a bit high there. There's a red mark that appears on the RPM target. I'm just going to slow down the system a little bit, just so I can get the RPM in the right range. Alright, so that's about right there. I'm going to click on plane 2. Right, now I'm going to ramp down the rotor and I'm going to switch to step 3. Okay, I'm going to slow the rotor. Step 3 is taking the trial weight and applying it to plane 2. So put it on plane 2 and it's in line with the marker from plane 1. So it's in line at the 0 degree position. So I'm going to do that. Now what I'm going to do is ramp up the system. So increase the speed, switch the impulse back to plane 1 so I can start my readings all over again. So the system's just ramping up now, approaching the right speed. Right, record plane 1, switch over to plane 2. Okay, plane 2. Take that reading. And ramp down. Switch over to plane 1. So now I'm going to go to my calibration factors tab. Click on that and click on the calibrate button. Alrighty, so what you'll see is an initial solution for the balance and also a series of factors. Now these things are called the calibration coefficients, and those coefficients are the mathematical model which defines your test setup. So I won't go too much detail into that. I'll click on done And what you'll find is those factors will now appear in the Advanced tab under this section here. Now it's probably a good idea at this point is to save your setup. So I might call this two, Dynex dumbbell motor driven 2, click on save. And what this does is it saves all your settings in a file, so you can actually open those settings at any time. Okay, so now we've calibrated the system. I'm going to remove the trial weight on plane 1, put that aside. So now we can actually run the rotor at speed and record the readings to perform the balance. So I'm going to ramp up to my test speed. Making sure that my plane 1 is selected. So I just allow the system to stabilise before I take readings. All right. So I'm now going to record plane 1, go OK, switch over to plane 2. All right, now I'm going to stop the rotor. So you can see in the software that for plane 1 and 2, the software determines the balance solution required. In this case, it's to add about 0.5 gram to plane 1 and about 0.042 grams to plane 2. Now that actually makes a lot of sense, because when I was running the rotor, by gently touching plane 1, I could feel a lot of vibration, but plane 2 was very, very smooth. So this solution does make sense, and we're going to apply that solution, run it again. Now, one thing to notice is that the quality limit for plane 1 and plane 2. So plane 1 has a very high value, and plane 2 a much lower value compared to plane 1. So what is the quality limit? As I discussed in the single plane tutorial, the quality limit is essentially the theoretical offset of the mass of the plane relative to the shaft. So for example, if I had 2 grams of a residual mass of that plane relative to the center of rotation, which is say 10 millimeters away, then my quality limit would be, or residual quality limit would be 20 gram millimeters. That 20 gram millimeters would be what we call the residual imbalance. So what we want to do is we want to apply the balance weight so that residual imbalance gets closer and closer to the center of rotation. As it gets closer and closer, that value for the quality limit will get smaller and smaller. So the quality limit that the software identifies for this particular rotor is around about 0.268 gram millimeters. And so we want to bring the values of plane 1 and plane 2 down to that level. So we're going to go ahead and apply the masses at plane 1 and plane 2 and run the rotor again to see whether or not we are within a reasonable limit. So again, I've got my jeweler scale. I'm going to measure out my 0.5 gram and 0.042 grams and apply it to the planes and see how we go. Okay guys, I applied the correction weights to plane 1 and plane 2, ran the solution again. So when I ran solution, I found that the the residual imbalance was still outside an acceptable limit. So I ran the solution again and got the new balanced solution and applied it. In fact, I had to do that 2 times to get an acceptable level. So in the software, you'll see that in the quality planes, they have both now turned green, which means that they're actually below the acceptable quality limit. Now, when I run the rotor, I can feel by touching the frames that it's very smooth. So I know that the solution is working and it's correct. There is a bit of art to balancing. A lot of it is to do with fine-tuning the position of the balance masses and also the location. Sometimes you have to tweak the location slightly, you know, left or right, for example, just so that you can get the right sweet spot. So what I'll do is I'll just show you what the final solution looks like. I'll just rotate around here. So on plane 1, you can see I had a number of attempts on the rotor. So the first attempt was a larger mass. This plane 1 was really out of balance. The second solution was this location here, which is the second highest mass. And these smaller ones here and here is more to correct the error associated with these larger ones. So plane 1 was really badly balanced. That was the key source of the vibration that I was getting. Plane 2, just moving around here. You can see plane 2 only required 2 correction masses, and these were small masses really to account for the fact that I had to add mass here. And sometimes that is to do with coupling effects. So an imbalance here will affect the balance on that plane and vice versa. So they're both coupled or related together. So there you have it, guys. That's the 2-plane balance method. It takes a lot to get used to. There is a bit of work involved in trying to set up the procedure and get it working. All right, so there you have it. That's the 2-plane balance method. A few things to note that sometimes when you try to balance and it's not working, it may not actually be an imbalance issue itself. There might be an issue related to the rotor itself. So, for example, there may be a case where the rotor on plane 1 is actually misaligned to the shaft, or the same associated with plane 2 being misaligned to the shaft. Some misalignments are very difficult to get right, and there may be other issues. For example, there might be a looseness between the connection between the rotor and the shaft as well. If you're having difficulty in obtaining the balance using the 2-plane method, what you can do is lock one of the planes. So, for example, I can lock the second plane here by actually restraining its movement from side to side, so that if I lock that and that is allowed to oscillate, if I do that, then I can actually attempt to do a single plane balance on plane 1. Once I get that right, I can lock plane 1 and try a balance solution for plane 2. Sometimes that gets you out of a bit of trouble. Either way, hope you enjoyed our tutorial, and if you have any questions, please list them down below. Thank you.